The complex logic gates or Boolean functions can also be implemented using basic logic gates. We will take the example of XOR gate and mux design here. XOR gate is similar to OR gate except that when both the inputs are high, its output is low. The symbol of XOR gate is shown here. When two inputs are given and one output is here. For two input A and B and output Y, the expression for XOR gate is written as Y is equal to A XOR B. Now we would like to realize the XOR gate. First we will try to write XOR truth table. It is almost similar to OR except that when both the inputs are high, the output is 0. We would like to implement this truth table using basic logic gate. As we see in Y, we are having at 1, 2 positions. When A and B combination is A bar B and A B bar. That means I need one AND gate to realize this and one AND gate to realize this, and either this will be true or this will be true, so we need one OR gate. The circuit implementation is shown here. So one AND gate, its output is A bar B. A is coming here. After this inversion it becomes A bar and B is coming here. Similarly, the output of this AND gate is AB bar. A is coming here and B is coming here, which becomes B bar after this inverter. Both outputs are going to OR gate, which gives me either this is true or this is true. The output at here can be written as A XOR B, which is simply equal to A bar B plus AB bar. This circuit can also be implemented using universal gates NAND or NOR. XNOR gate. XNOR gate is simply an XOR gate with an inverted output. The truth table for XNOR gate is given here. When both inputs are similar, the output is 1. When both inputs are different, the output is 0. This is the symbol for XNOR gate. This bubble shows it is XNOR. The expression for XNOR gate is not of A XOR B, or we can also write Y is equal to A bar B bar plus AB. What are the applications of XOR gate in our life? A very common use of XOR gate is to compare two inputs A and B. To compare two inputs A and B, we have three conditions. Either A is greater than B, or A is less than B, or A is equal to B. In bit terms, we have A greater than B when A B bar is true. That means A is 1, B is 0. A is less than B when A bar B is true. That means A is 0, B is 1. Or A is equal to B when either both are 0, 0 or both are 1, 1. So AB means 1, 1, A bar B bar means 0, 0. To prove this condition, we need XNOR gate. To prove these two conditions, we need XOR gate. In addition to comparing two bits, XOR gate is very commonly used in arithmetic operations. Mux design. Mux is also a very important combinational circuitry. Mux gives one output from many inputs. That means it is the selection circuitry. We have to select the output for given many inputs. Here we have few type of multiplexers like 2:1, 4:1, 8:1, 16:1. That means I have 2 input, 4 input, 8 input, 16 input, and out of that we have to select only one output. Now we will take the example of simple 2:1 mux. Mux has three components: inputs, selection lines, and outputs. In 2:1 mux, we have two inputs A and B, one select line S and one output line Y. A and B are one input, Similarly, S is also of 1 input and Y is 1 bit output. Now, the implementation is like that. If my select line is 0, I have to pass A to Y. When my select line is 1, we have to pass B to Y. How to realize this circuitry? So first we will make the truth table of both the options. When S is equal to 0, I want to pass my input A to Y. So this is 4 combinations of 2 inputs, and when S is equal to 0, this A is passed to Y. Similarly, when S is equal to 1, we want to pass B to Y. So when S is 1, this B is passed to Y. Now by combining these two tables, we can write a single truth table for combinations of A and B. So 4 combinations for S is equal to 0, then 4 combinations for S is equal to 1, and we write here output depending upon my select line. When select line is 0, A will be passed here. When select line is 1, B is passed here. To implement this, we have to find out at how many places we have 1 in my output. This combination is when S is equal to 0, A is equal to 1, S is equal to 0, A is equal to 1, B may be 0 or 1. Similarly for this one, B is 1, S is 1, here B is 1, S is 1, A may be 0 or 1. So to implement this one, we need S bar A. Similarly, to implement this logic, we need S B. So 2 AND gates are needed, which gives me S bar A and S B. This is my select signal. If we put one inverter, it will give me S bar. Now these two logics are given to OR, and it gives me S bar dot A plus SB. So when my select line is S, A will be passed, that means this will be passed here. When my select line is S is equal to select line is 0, A will be passed. When select line is 1, B will be passed to output. What are the use of these mugs in our daily life? Here is one very simple example. We have 2 computers and single printer. Now both the computers we want to connect to this printer. So we need a switch type of devices. When switch is A, first computer is connected to printer. When switch is at B, second computer is connected to printer. This logic is here marks. Many this type of examples we need in our daily life.